Hi everybody, welcome back to Chem 163. Today, the magic word is buffers. What the hell is a buffer? A buffer is probably the most important thing in this class. I mean, besides acid-base chemistry. Oh, excuse me, hold on. Sorry, I had to cough there. A buffer is probably the most important thing physiologically, as buffers are what prevent us from dying due to exposure to acids and bases. So we're going to talk about those today. What agenda items are on the docket here? So the quiz for Chapter 14 is due tomorrow. So turn that in on Canvas. It will be closing on Friday night. You can also turn in the paper copy during the exam on Friday. Speaking of which, there is an exam on Friday. Please come to the lab. Please do not be late. We will take the exam in the lab next door to where we normally have lab, because it has chairs and seating, and so you can sit down and take the lab in there. I sent an announcement about the exam, so make sure you read that. And yeah, let's get started. So let's talk about buffers. What is a buffer? A buffer is a solution that does not exhibit as much of a change in pH as we would expect it to. And the way that this happens is that when we add strong acid or strong base to the buffer, it neutralizes those quantities. So we'll just highlight that right here for you. Now, how the heck does that work? In order for us to understand how a buffer works, we need to understand what a buffer is. A weak acid is the first component that we need for a buffer. You can pick any weak acid you want. What you cannot pick is a strong acid, so no HCl, no HBr, no HNO3, but HNO2 would work because HNO2 is a weak acid. So any weak acid that you can come up with. Then what you need to do is you need to pair the weak acid with its conjugate base. Now, of course, the reverse of this is true too, because you can pick any weak base you want and its conjugate acid, and that's still valid. But what this ends up doing is that the weak acid that you chose will react with any base you put in there, whether it's weak or strong. The strong base will just get instantly neutralized by the weak acid. If you add any acid, strong acid, that will react with the weak base that you have in there. Now, interesting, what you are doing is you are creating a pair of substances that does this. So here's our weak acid, and here's our weak base. And if I react with the acid here by, say, doing this, I would then create this thing in the solution. But then if I reacted with the acid, it would just go right back. And so what I have are two substances that just react with each other. They go back and forth and back and forth and back and forth. And this is a buffer. A buffer just changes back and forth and back and forth and back and forth. The H plus just hops from the weak acid to the weak base. And thus, we just have these two substances in the solution, and the pH is whatever it should be for having roughly half and half of this, which we're going to find out is something that we can calculate extremely easily. All right. Now, we have to have both of these things. If you only have a weak acid and you add acid to it, then the pH of your solution will be whatever the strong acid is. Because remember, when we have a mixture of acids, the pH is whichever of the things is stronger. So a weak acid cannot resist strong acids. It would only resist strong bases. So I have to have both components. So our first little discussion here is going to be, can you make a buffer out of these? So could I put hydrochloric acid and sodium chloride to make a buffer? Well, no, of course you couldn't. HCl is not a weak acid. But what about this one? Would this make a buffer? I'll give you a minute to think about it, and then we'll explain yes or no. All right. Hopefully you've thought about the answer. The answer is cat. Yes, the cat just jumped up and wants me to pet her. So, first of all, we have to identify a weak something. So this is a weak base. And this is its conjugate, weak acid. So, this will form a buffer. Cat is always the answer. I'm actually not sure that I fed the cat. I thought I did, but sometimes I am just forgetful. All right. Now, could I form a buffer out of these? So this is a weak base, and this is a weak acid, but they're not conjugates. And what would end up happening here is that I would likely form a salt. This would just pop over here, and I would make NH4 C2H3O2, and then it would just kind of hang out like that. So, in order for us to have a buffer, we need to have conjugates. Otherwise, they just react. The two parts of the buffer, quote unquote, that we were trying to make. All right. Please don't sit there and meow at me. Stop that. Stop that. Stop that. Oh my goodness. It's not working. I'm trying to make her stop. Ah! Now she's right up on my lap. Stop. No. Maya, go away. All right. This is a pictorial version of what a buffer looks like. I'm trying to shoo the cat away. Oh, she finally left. Okay. So if we mix these two things together, we will have a buffer where I have, again, my weak acid and then a weak base, that is the conjugate of my weak acid, in the solution. Now, what we can do here is we can say, okay, I'm going to add a strong acid. The strong acid will react with the weak base to get neutralized. And then the strong base will react with the weak acid, and it will get neutralized too. If it's neutralized, it can't affect the pH, right? What does HCl become after you neutralize it? Well, if I neutralize it with whatever, it becomes Cl minus, which is pH neutral, and then this H would be whatever is neutralized by it, like H2O or something, right? So once you neutralize it, it's gone. And it doesn't affect the pH. At least it doesn't affect it as much as it would if it were the strong acid or the strong base. Now, there is some impact on the pH, and we're going to see why that is. Because as I react the sodium acetate, it turns into acetic acid. And if I have the same amount of both of them, I'll have some pH. But if I have different amounts, my pH will slightly change. All right, so there's our reaction of the hydroxide reacting with our weak acid here. So here's our hydroxide. It's going to react with this. I will create acetate, which is already there in the solution. So whatever pH change we see is going to be very tiny. And then here's the same thing for our acid. When acid reacts with the weak base, we create the weak acid again. So it's in this manner that buffers resist pH changes. Because really what you're doing is you're taking something strong and turning it into not only something that's weak, but something that's also already present in the solution in a fair quantity, because we've prepared the buffer. And so the change to the pH will be negligible for small amounts of strong or weak or strong acid or base added. All right. So there's our summary. Buffers will resist changes in pH. We need to have both a weak acid and its conjugate weak base. The weak acid in our buffer neutralizes added strong base, and the weak base in the buffer will neutralize strong acid. Sweet. That's the logistics behind it. So I think on the next slide, yeah, here we go. I have a bunch of these, and what I want you to do is tell me which of these will make buffers of the first 4 here. 1 through 4. And then for number 5 down here, I want to make a buffer that contains hydrocyanic acid. What would I use as the conjugate? What would I also mix in? So I'm going to give you like 3 or 4 minutes to think about these. Type your answers in the chat. We'll go over the results in just a second. One or two more minutes. We'll go over the answers. All right, we're back. And I discovered I was a bad cat dad, and I didn't feed the cat. Well, cats. I have 2 of them. All right, so for number 1 here, I have sodium bicarbonate, which is actually just this ion, right? And I have carbonic acid. Will this make a buffer? Yeah, it will. They are conjugates of each other, and they are both weak. How about the second one? So this is phosphoric acid, which is a weak acid, believe it or not. And then we've got dihydrogen phosphate. So this will also form a buffer. Phosphoric acid, not a strong acid. A lot of people think it is, but it's not. It is definitely stronger than most weak acids, but it is still a weak acid. All right. This one down here, no good. This is strong. Strong acids don't form buffers. The reverse reaction can't happen. This is a weak base, so this is pyridine. That's okay if you don't know what that is. What you should notice is that, oh, it's got nitrogen in it. It's probably a weak base. And then if I add this HCl to it, the Cl is just a counteranion because the weak acid part is this part. And just like before when we were saying, oh, it's sodium plus, nobody cares. Oh, it's potassium plus, who cares, right? We just do that with the chloride here too. If you need an ion to pair something with so that it's electrically neutral, pick Cl if you need a negatively charged ion. If you need a positively one, pick sodium. In fact, that's what we're going to do down here. I have HCN. If this is HCN, what would its conjugate be? Well, it'd be this. So what ionic compound would I use? Well, I can't just buy cyanide, right? You can't put something negative only in a bottle because it would just all repel itself, right? It wouldn't make an ionic compound. We have to pair it with something positive. So you would actually buy sodium cyanide instead. Or you could buy potassium cyanide, so this is allowed. Or this, or whatever, right? You could pick any one you want to, but honestly, everybody would pick the sodium one because sodium is the most abundant. It's cheap. All right, so that's what buffers are. Let's do some calculations with buffers. Now, if I were to take a 0.1 molar acetic acid solution, I could calculate its pH. That's pretty trivial. We've done 74 billion of these problems, right? We'll set up the ice table. We'll solve for X. X is H3O plus. We negative log it. Hopefully that's trivial because otherwise tomorrow, or not tomorrow, but otherwise Friday is going to be a real struggle if we haven't mastered our ice tables. Likewise, we could do the pH of a weak base like sodium acetate. We just find the Kb for acetate, write out the ice table, set up the Kb expression, yada yada yada, solve for X, that's hydroxide, get the POH, get the pH. What the heck do we do when we have both things, though? What if you have a mixture? How do you solve this? And the answer is, it's not that much different. So let's do that. So the mixture of both of these things should be higher than just the weak acid, right? Well, how do we solve it? How do we figure out what the pH of a mixture of this is? That's what I'm trying to click on. There we go. So I'm sort of anticipating that the question is going to ask us this, but that's okay. So what we're going to do, I want to make sure I get the right sig figs here. So we've got our acetic acid and sodium acetate. And remember that really this, we don't care about this. This is really just this, right? So what I'm going to do is I'm going to write the reaction for the weak acid. I've been always putting the H2O first, so let's do that this way. Okay. And then what we're going to do is we're going to make our ice table. And normally we just cross out water, which is still what we do. We'd say, okay, well, I've got 0.100 of the weak acid I'm starting with. I've got essentially none of this. And then we'd put a 0 here, right? But guess what? We totally have this in there. That's literally the only change for buffers. Ah, it's the same thing we've been doing all over. Oh no! But, I mean, that's great, right? So, we're going to use up this for the reaction as written. We're going to lose that. We're going to make this. I should put it up here. We're going to make this one too. And then I have the Ka for acetic acid memorized, so it's just this. So, well, since this is an acid dissociation, we could say Ka equals the hydronium and the acetate divided by the acetic acid. I don't know how to numbers today, I guess. There we go. And so that's just going to be this. It's not x squared anymore because I have this crazy term here. And you're going to notice something very interesting happens. So remember, x is small. We can do that here, but we can also do it up here because 0.1 minus a tiny number is still 0.1, but 0.1 plus a tiny number is still 0.1. So now I have x times 0.1 divided by 0.1. So these then cancel. And I get this. Which equals the amount of H3O plus. So that means that the pH would be equal to minus log of this number. And what does that mean? What? We could just look up the pKa. That's the pH. But only if both components of the buffer are equal. So what is the pH of a 0.1 molar sodium acetate buffer with an acetic acid 0.1 molar solution? So both of them are 0.1. What's the pH? It's equal to whatever the pKa is of the weak acid that you picked. This is why I picked the weak acid, by the way. So that's going to be super useful for us. Now, if I were to change these numbers, then I can't do this step right here, right? So if I cancel these two numbers out, I get x equals Ka, which is how I get pH equals pKa. So these do have to be the same concentration. But if I change these other numbers in any direction at all, I will get a slightly different pH. So we're going to use this type of relationship between the weak base and the weak acid to create a formula in just a little bit. That's going to save us from having to do ice tables for buffers because we just reduce it. All right. Now, the rest of this slide is talking about how, well, if I make this number bigger, or like anything, just the fact that it is in here in the solution means I get a different result for my pH. Like if I was just a weak acid, I get like a pH of 2, but instead I got a pH of 4. I did not produce as much acid. And the reason for that is because if this is already there due to the buffer, that'd be this one, then the reaction is driven back towards reactants. And so this is called the common ion effect. We're going to see the common ion effect in Chapter 15 a lot, because we can salt in and salt out stuff. For example, if I don't want silver chloride to precipitate, I can add sodium chloride. That increases the amount of chloride already dissolved in the solution and would form it back into AgCl. I think I might have misspoken earlier, but I don't want silver chloride to dissolve. That'll make more sense in Chapter 15 when we talk about KSP. So don't worry about that too much for now. But the common ion effect is basically just Le Chatelier, because I have this number here, up here, this number right here. If I put a 0 down there, you could probably see that our reaction, we wouldn't have this 0.1 on the top, we'd have an x squared. We'd get some number for x, and that would be a much larger number because all the stuff gets canceled out here. All right. Oh, look, we already did this. Okay. Now, just to prove that pH equals pKa, I'm going to take negative log of our Ka. And when I hit this button, what do you get? You get 4.74. Look at that. Okay. Now, what I want you to do is I want you to do this same buffer. So this is going to be acetic acid and sodium acetate. But I'm going to give you different numbers. So instead of getting Ka equals x, you're going to get Ka equals some ratio of these numbers times x, because all the other x's are going to drop out of the equation. So go ahead and try this, and I want you to tell me what the pH is. Now, without doing the problem at all, like right here, let's see here. Will the pH be greater than or less than 4.74, which was the pKa? So without even doing the problem, you should immediately know the answer to that based on what I've highlighted. So when you do your calculation, you'll know, oh, I should get a number that's smaller or bigger or whatever. So I'm going to leave you 4 or 5 minutes to do this problem, because I guess we haven't done enough weak acid problems. And then we'll show you the Henderson-Hasselbeck equation. You'll never have to do that again. All right, one more minute. We'll go over the answers. All right, so let's go over here. So I'm just reusing the table that I had from before, and we're going to just enter in the numbers. So for my acid, I have 0.200. I have essentially no hydronium before the reaction occurs. But for our base, we actually have stuff in there too. And then same deal as before. Let me try that again. We get that. So those are our concentrations at equilibrium. And then when I go down here, I get H3O, so that's X. I get acetate. Divide by acetic acid. And then what we can do is we could say, well, X is small. So subtracting it from a much larger number isn't going to change these numbers. And so now what we get is we get Ka equals X times 0.150 over 0.2. So I'm just going to flip that and move it over here, right? And so what does that equal? So here's Ka. Ka is 1.8 times 10 to the minus 5. And then we'll times it by 0.2, divide by 0.15. So it's going to get a little bit bigger. There's my pen. So and we said above here that H3O plus was what X was. So the pH must be minus log of this number, so log minus. All right, so the pH is slightly lower. Why is it slightly lower? Well, we had slightly more acid. This one right here, right? If I had more base, the pH would be slightly higher than whatever was the midpoint. All right, that's easy enough. Now, here's a more common type of problem that you're going to see for buffers. And it's not the ice table that's the issue. The issue is going to be, well, shit, I'm mixing stuff. What do I do? So we're going to do this question together. What is the pH of a buffer that forms when I take 60 milliliters of 0.250 molar formic acid and 20 milliliters of 0.500 molar sodium formate? Because if I want to make a buffer in the bio lab, I don't go to the shelf and grab the buffer that's pre-made. Generally, chemicals tend to stay more stable if they're just pure, not pure, but I mean they're just only one thing in the solution, right? So we don't have like 7 things floating around in it. So I would prepare the buffer for my needs. Maybe I don't want pH 5.2. I want pH 5.1 or 5.0 or 4.9 or whatever, because I'm trying to test something. So being able to make our buffer is a lot more practical. So we need to understand how to actually make buffers and get pHs that we want out of them. So, okay, we're going to make 60 mils of this with 20 mils of that. So let me get this on the screen here. And that hint at the bottom, I'm going to leave that on the screen for just a second. I mean, I know this, but this is going to be really crucial to how we figure this out. Because at one point, or at some point in this problem, you're going to be like, oh, okay, duh, and now you know how to solve it. And so, whenever you mix two liquids, oops, I got to move this over just a little bit. Whenever you mix two liquids, you bust out this formula, right? So what we're going to do is we're going to say, I'm going to dilute these two things by mixing them together. Now, they're both aqueous solutions, so that we're going to assume their volumes add. I know in the past I've said, hey, volumes don't add if they aren't exactly the same solution. And the amount of sodium formate relative to water in these solutions is so negligible that any volume change from us not having the same solute is not going to be discernible to the number of sig figs we're using. So as long as both of the solvents are the same, it'll be okay. So let's look at this for the formic acid. So the molarity of the formic acid before I dilute it was 0.250. And I'm putting in 60 milliliters of that. When I'm done, it will have a total volume of 80 milliliters because of the 20 from the other component. And I got to solve for this. So we'll just set up the equation. Our volumes will cancel out. And our concentration after the dilution will be that times 60 over 80. 0.188. So there's our formic acid concentration after we've mixed them. And so we could do the same thing for the sodium formate. So what's its initial concentration? It was 0.500. And I have 20 mils of that. And the final volume when I'm done diluting will be 80 mils. And so we'll just do the calculation again. And so that'd be 0.5 times 20 mils. I realize I didn't really budget my space here super good. I should double check that. I'm pretty sure that that's right. Times 20 over 80. Yeah, okay. And so that would be my sodium formate solution. So now that we have the correct molarities, we can do the buffer process here. If only I had enough space, right? Well, we could just cram it in here. So we've got formic acid and water makes H3O plus and formate. And again, we don't care about water. And we just use the numbers that we had. So up here I had 0.188. Essentially nothing. 0.125. We let our reaction go. And you can basically do it from here, right? So we'll say Ka equals X times 0.125 plus x. There we go. We'll get rid of these x's because x is small. And so Ka, or x, will just be 0.188 times Ka divided by 0.125. And so we'll just do that in the calculator here. So 1.8 times 10 to the minus 4, that's Ka, times 0.188 over 0.125. So we get that. And so the pH of this must be there you go. So we really crammed that into the corner here, but that's okay. So really, the only new thing that we had to do is we had to do this dilution stuff at the top here to figure out these new concentrations. And then after that, it was just a buffer ice table. Any questions, let me know. All right, so when we get back from the break, what we're going to do is I'm going to give you an equation. Oops, sorry, I accidentally tabbed forward there. I'm going to give you an equation that is going to prevent the need of having to do an ice table for any buffer. Doesn't that sound nice? Instead of doing the ice table, you just plug this into this equation, and this spits out an answer. So, yeah, you'll get to see that in about 10 minutes. So, come on back after your break. Go and pet a cat. Go and feed the cat. I already fed the cat. Go get some more water, or just chill out and listen to some more Mega Man 9. We'll see you in just a little bit. Alright, there we go. Welcome back from the break. I hope your cat is happy. Alright, here's your equation. This is the Henderson-Hasselbeck equation, also known as the HH equation because we get sick of saying Henderson-Hasselbeck. It's just too many syllables. So we're going to use the HH equation to predict the pH of any buffer following some restrictions. So first, let's explain the equation. So pH is what we're solving for, but pKa, we know what that is. So the pKa is going to be for, it's the Ka. So we need to know what the weak acid is, and we need to know its Ka. This right here, this is going to be the concentration of the weak base component of the buffer, and this is the weak acid component. So if we were doing the previous example, which was all of this nonsense over here, remember all this that we just did? We got 3.57 as our answer. So what we're going to do is we're going to type this in the calculator and see how close we get. So we'll say, so what's the Ka? The Ka was 1.8 times 10 to the minus 4. So pKa would be 1.8 times 10 to the minus 4. We're going to minus log that. And then we're going to go, my equation isn't on the screen here, so you can't actually see this. Oops, I accidentally negated it again, so we'll make it positive again. Okay, so that plus parentheses log of base over acid. Well, the base was 0.125, and the acid was 0.188. We're gonna close that parenthesis. We're gonna log it, and then we'll hit enter. And look how close we get to the answer. So now all we need to do is the dilution part. Look up what Ka is, find the pKa, and punch it all in the equation. So this is fantastic. This makes our life so much easier with buffers. Now, there's actually two caveats. The first caveat is this has to be X is small valid. So if the X is small approach does not work, then we have to solve using Wolfram alpha. And the reason that this requires the X is small approach is because the base is really going to be the base, whatever the base was, I don't know, say this, plus X, and this would be minus X or whatever. So when we scribble this out, we get just the base over the acid. Now, if you're not allowed to scribble it out because X isn't small, then you have to use a solver. Now, there is one other stipulation, and that requires that the base and the acid be within a certain ratio of each other. If you have too much of one versus the other, what ends up happening is you don't have a buffer anymore, and then this equation falls apart because, again, X isn't small. So let's find the pH of a buffer solution that is 0.060 molar benzoic acid and 0.150 molar sodium benzoate. And then here's Ka. So let's write down the HH equation. Not equals, that's not what I meant to write. And so now we'll just plug in all the numbers. Well, pKa is going to be minus log of 6.5 times 10 to the minus 5. So that's pKa plus log of base over acid. Well, this is the base over the acid, which is this one. And so we get 6.5 times 10 to the minus 5. We're going to log minus that plus parentheses 0.150 over 0.060. I don't know why I'm typing this in. Well, I have a bunch of buttons to push. There we go. So we'll do that, and then we'll hit equal. And we get this. Could not be easier. All right. So this is going to make our base, or not base, our buffer calculation so much easier. Now, what if you want to absolutely be sure that this is a valid approximation? What you can do is you can find out how much H3O plus you have from the pH. So that would be 10 to the minus. Oops, I got to do it this way on here. So 4.58 was what we got. So we'll negate that. We'll go 10 to that. So that's how much H3O plus I had. 2.6 times 10 to the minus 5. We'll divide that by the weak acid. 0.150 times 100. So we weren't even close. 0.017%. So totally valid for this problem. All right. Here's the other condition that we want to make sure we satisfy. To make sure that our X is small approach is valid, the amount of acid that you have needs to be about 100 to 1,000 times bigger than the equilibrium constant. So what that means is that if you have something that's like 10 to the minus 5 and you're working with 10 to the minus 1s, like 0.1 would be fine. 0.2 would probably be fine. 0.01 would probably be fine. But 0.001, that's kind of getting into the gray area. And if your solution is too dilute, then you just have to use a solver. All right, let's do some more of these. Now, sorry, hold on a second. I need to drink more water. Oh, no, I'm out of water. I can fix that in a second. Now, what we're going to be doing now for this next section is that we are going to be adding strong acid or strong base to our buffer, and that's going to use up some of it. Now, in order to calculate changes in our reaction, or in our buffer, due to the reaction of strong acid or strong base, we're going to have to make a new type of table. So we're going to use what I'm calling a before-after table. And we only use this before-after table when we are reacting with a buffer. Okay, so don't make this your substitution for an ice table. Ice tables are for equilibrium. This is not an equilibrium. We're using a strong acid to neutralize part of our buffer. It is a reaction. So we're going to make a before-after table, and it's going to look like the ice table, but instead of writing ICE, I'm going to write B, A, and then a delta in the middle. All right. So let's do an example of this, and I'm going to draw out, I'm going to do my own before-after table so that we can see this in action here. So we're going to have a buffer, and our buffer has some volume in it. We don't really care about the volume. What we care about are the number of moles of the buffer. So I'm going to add 0.025 moles of HCl to my buffer. So first, let's write out the reaction of the buffer with the HCl. Now, this is an acid, which means that it will react with what part of the buffer? It's not going to react with the acid, right? It's going to react with the base. So I need to write that. So here's my base reacting with HCl. And that's going to form Oops, not minus. Sorry, that shouldn't be there. That's going to form this. And the Cl minus is just going to hang out, but we don't really care about this. Because that's not part of the buffer that we're going to calculate. It's pH neutral. So we'll just ignore it. So what we'll do is we'll make a table, and that's going to look like this. So before, we're going to change stuff, and then after. Now, before any reaction occurs, I have this many moles of base in my buffer. I also have this many moles of the conjugate weak acid. I don't have any HCl in there because I haven't done anything with it yet, right? Now, my change is going to be I'm going to add this many moles of acid in there. What does the acid do to my weak base? Well, it's going to subtract from this, right? What will that do? Well, the reaction of this will produce this one, won't it? So I'm going to subtract these numbers. 0.1 minus what HCl I put in there will be that. 0.1 plus whatever amount of HCl I put in there would be that. And I am just subtracting this number from that and adding it to that. Because I'm adding HCl, it will react with the weak base, and the result becomes the weak acid. Now, if I wanted to calculate the pH of this, I would just use the Henderson-Hasselbeck equation. So I'd have to go look up the pKa for acetic acid. That's easy enough. Plus log of base over acid. Well, wait a second, Professor West. We don't have concentrations. We only have moles. Okay, well, I'm going to divide by some volume then, whatever the volume is to make it a molarity. And when I put it in here, this is what will happen. Well, here's my base over the acid. Oh, look, they cancel out. So if you just want to put in moles in there, you could totally do it. The volume's not going to change it. And then we just look up whatever the pKa is, and we can solve for the pH. So that's easy enough to do using this before-after stoichiometry table. So if I give you a problem on exam number 2, or quiz 15, we'll say, more likely that's what you'll see first. Look at what you are reacting with your strong acid or base. Make a table like this, and then you have what you can throw into the Henderson-Hasselbeck equation. That's just wrong end of the pen. That's just these right here. All right. So this is more or less the same thing that I just showed you. And there's our new values that we use to determine the pH. So let's do another one of these. Oh, no, let's look at a visual, I guess. I mean, this is kind of a not super helpful here, but if you wanted to visualize what's happening to the amounts of stuff in your buffer, if I add acid like this, that's going to react with this, because there is an acid on there, so I use up some of them. I still have a buffer, though. If I add hydroxide, that's going to react with... Oops, sorry, not there. That's going to react with this one. And do that change to it. So, all right. We already know how to do all this. So whenever I give you a buffer problem where I say I add this much HCl or this much sodium hydroxide to it or whatever, I'm trying to react with the buffer, you're going to use the before-after table to figure out the new moles of your buffer components, and then you can plug those straight into the HH equation. So let's do that. I have 1 liter buffer. I have 1 mole of acetic acid, 1 mole of sodium acetate. The initial pH is 4.74. What is the new pH after 0.010 moles of solid sodium hydroxide is added? Assume the volume is not changed. You're not going to have to worry about volume at all for this problem, so don't worry that I put 1 liter there. We're just going to plug it straight into the Henderson-Hasselbeck equation, and it'll be all right. We are going to care about volume later, because what we're doing now is going to set us up for the titration part, which we're going to do on Monday, and then we'll finally be done with Chapter 14. Right? Seems almost too good to be true at this point. But what I want you to do is I want you to try and tell me what the pH will be. Now, you're adding sodium hydroxide, so the pH result should go which direction? You should get a number that is higher or lower than 4.74. I'll give you 5 minutes to play with it, and then we'll go over the answers together in just a bit. One more minute, we'll go over the answers. All right, so let's go over here. Oops, I need the Ka there. I'm in the wrong window. There we go. All right, so I'm reacting with sodium hydroxide. So NaOH is added. Now, sodium hydroxide is a base, which means that it will react with the weak acid in the buffer. So we're going to write that reaction. So we're going to say sodium hydroxide. Oops, let's do the sodium hydroxide second. So what is the weak acid in the buffer? That is the acetic acid. That's going to react with our sodium hydroxide. We're going to form the acetate. And we make water, but nobody cares because water is neutral. So let's make our before-after table. So before, after. Why does before get abbreviated when it's only one more letter than after? You know what? I don't know. Let's fill it all in. All right, so I've got 0.1 moles of acetic acid and 0.1 moles of sodium acetate. And I'm going to add 0.010 moles of sodium hydroxide here. That's going to react with this, so I'm subtracting. That's going to produce this, so I'm adding. So this is going to become 0.90. This is used up. This is going to become... You know what? I don't want to write a dash. I don't want that to look like a subtraction. And that's going to become that. So that's the number of moles that are in my solution now. So now I can write the Henderson-Hasselbeck equation, which will be pK plus log of base over acid, which should be, well, Ka is 1.8 times 10 to the minus 5. We're just going to do that. So pK is 4.74 plus log of the base, so that's 0.110, divided by the acid, which is 0.090. And remember, if I had volumes here, I could do this to get a molarity, but those would just cancel. They're the same volume, right? So we'll say 4.74 plus log of base over acid. So that's 0.110 over 0.090. And we have to hit log on that, and then hit enter. All right. The pH slightly went up. And that makes sense because what did we add to it? Well, we added hydroxide, right? So if I had a base, the pH should increase. And it totally did. Now, did it increase as much as it would have if I had just made a solution out of 0.01 moles of solid sodium hydroxide? Just to check that, if I had a 0.01 mole solution in 1 liter of water, what would the pH be if it was just the solid sodium hydroxide? Well, I would take the negative log of that. That's the POH. And I had Subtract that from 14. This would be the pH if it was just the sodium hydroxide. So that sodium hydroxide on its own had the potential to be pH 12. So instead of raising the pH from 4.7-ish to 12, it went up to 4.83. So we have resisted a huge change in pH. If this was your bloodstream, your body would be very happy because pH 12 would kill you instantly. All of your proteins that were essential for life would completely denature almost immediately. And interestingly, I had forgotten that I actually asked to do that problem. What is the pH when you do this? Yeah, it's 12. So buffers are crucial for your health. Because what's the first thing your body has when you eat stuff? It's your stomach, and your stomach is pH 1 or so. It's like that so it can dissolve stuff. If that acid got into your bloodstream would also be pH 1. And that's no good because proteins can't handle that. They would denature. We'll talk more about that in biochemistry. Well, I mean, I won't talk about that. I don't teach biochem. Not for biology majors. You're gonna learn that in much more detail in bio. I want to say it's 221. I don't remember the numbers. It's cell bio though. All right. Now I have this written here that the volume changes. And that's going to be important if we were using molarities to like do an ice table, but in reality you don't need to worry about the volume here. So, and there's a specific reason for that. So I want you to play around with this. We're adding HCl now. Tell me what the new pH will be afterward. And, you know what, just don't worry about this. Because when you make your before-after table, it's still all going to be moles. But how many moles of HCl did I add? You're going to have to figure that out for me. We'll come back in 5 minutes. So give it a shot. One more minute, we'll go over the answer. All right, let's look at the solution. So I got to clear this again. Boop. Oh, I do need Ka. Actually, I don't really need Ka. That's the Ka I have memorized. Because my brain is full of stupid constants. All right, so we are working with the same buffer. We're going to add 10 milliliters of 0.10, 1 molar HCl, actually. And so we need the number of moles that has. So if I have 10 milliliters, that's going to be that many liters. And that's the definition of molarity. So I have that many moles of HCl. Hooray, it's the same problem we just did, just with a different number. But this is an acid, so we're going to react with the base. So we need to write out the base expression here. And then don't care about this because it's neutral. And now we'll make our before-after table. So before, after. So I had 0.1 moles of this, 0.1 moles of this, and we added 0.0100 moles of this. Really, this sig fig isn't going to matter because it's not present here. We're going to reduce this by reacting with it. We're going to add to, oops, that was a little off. There you go. And then we can Henderson-Hasselbeck. Oops, sorry, you can't quite see that. Ah! Oh, for fuck's sake. There we go. So pH equals pKa plus log of base over acid. Really, the part that's going to get everybody mixed up is this part right here. Make sure you put the numbers in the right spot. That's really the crucial part. So pKa of this is still 4.74, because we just did that in the previous example, plus log of, now this arrow's in the way, I gotta get rid of that. So which one is the base? The base is this one. Oops, I almost erased it. So that's my base. So that's going to go on the top. Over the acid. And then those units cancel out. Oops, those units cancel out. And then we just punch it all in the calculator. And we should get a smaller result. I can tell by just looking at that because log of a number smaller than 1 is negative. So I'm getting a negative number, which will then be subtracted from this. So I'll get 4 point something less than that. So 0.090, oops, 0.110. So that's my inside the log. I'm going to hit log, and I'm going to add that to 4.74. 4.65. Remember that the number of sig figs inside here is the number of decimal places you get, so that's why I'm keeping these 2 decimal places. Again, I don't really care too much about sig figs for logs. I'm not going to grade you on that. When you're doing pHs, just do at least 2 decimal places. You'll be fine. All right. We've done enough calculations with buffers to understand them now, I think. So let's talk about some more practical stuff using these equations. What if I give you a buffer where I have a weak base as like my main focal point? I.e., I know what the pKb, or I know what the kb of the base is. Now, the equation, unfortunately, uses pKa, right? Now, there is a pKb equation, but I don't like using it because then people get that mixed up with the pKa equation. I'm going to give you the pKa equation anyway, but there's a really convenient relationship between pKa and pKb. Well, you know that Ka times Kb is Kw, right? If I played with a bunch of logs, I could show you the proof for this, but really, it's just this. pKa plus pKb equals pKw, which is 14, because minus log of 10 to the minus 14 is just 14. So if you know one of these things, just do 14 minus it to get the other one. And vice versa, right? So for a lot of bases, like ammonia versus ammonium, we're going to do the ammonia-ammonium buffer in just a second here. The pKa is not memorized by most people, but Kb is known. And so we can look up what Kb is, find pKb, and then find pKa. So we'll do that on the next slide. So let's do that. Using the HH equation, what's the pH of a 0.45 molar ammonia and a 0.25 molar ammonium chloride buffer? First of all, is it a buffer? I got a weak base, and here's its conjugate weak acid, so yes, it is a buffer. So let's find this out. So let's write out the equation first. And then I know that Kb is 1.76 times 10 to the minus 5, which means pKb would be minus log that number. So 1.76 times 10 to the minus 5. We're going to log that and negate it. And then we know that pKa is just 14 minus that. So I'm going to go do. That should have been a 5, but I did not pick my pen up. So let me fix that. Okay. So here's our expression. So this will be 9.25 plus log of base. So here's my base over the acid. They're both molarity, but those cancel out anyway. And we'll just punch it in the calculator. So 0.45, 0.25. That's what's in the log. Log plus 9.25. 9.51. Wow, this is so much easier than ice tables. Isn't it great? Thanks, Henderson-Hasselbeck. All right. Now, resist the urge to throw this equation around everywhere because remember, it only works for buffers. Nothing on the test that you're going to do on Friday is a buffer. In fact, I'm not even putting the Henderson-Hasselbeck equation on your exam. So don't fall for the sneaky tricks and resist the urge to just throw this around everywhere. This only works for buffers. In the next section that we're going to do when we come back next week, when we do acid-base titrations, we're going to calculate the pH at like 70 billion points to make a pH curve. We're going to have to use both the ice table for equilibrium expressions, and then the Henderson-Hasselbeck equation with a before-after table at different points. And we don't use them at the same time. We use them at different times. Now, all of that said, if you just hate the Henderson-Hasselbeck equation, maybe you hate people who have H as the first letter in their name, in which case, why are you in my class when my last name is Hillman? And you just want to do ice tables for days, you could totally do an ice table for all these types of problems. But, like, why bother at this point, right? Work smarter, not harder. All right. This is the same exact problem because it's the same buffer, so I'm going to just skip this. But you could do this one on your own because you're just literally changing. I already erased it. You're changing the numbers in the base of your acid. Do we have another buffer? Oh, that's a different problem. That's good, though. Yeah, I'll have you solve this problem. Okay. So there's my buffer above. So I'm going to add 0.010 moles of sodium hydroxide to it. Tell me what the new pH is if the volume doesn't change. So there's my pH before we've added it. Go ahead and do this problem. I'll give you 4 or 5 minutes. We'll go over it together, and then we'll be out of time. So it'll be a good place to stop. All right, we're almost out of time, so I am going to solve this for you. All right, I do need this KB. So we'll put that on there. All right, so we are adding... Oh, I lost my stylus. There we go. So I like to do the table just so that I can see where the numbers are coming from. You can totally do the mental math if you want to, but just be very careful about it. We might be using numbers later on that are much more complicated. So just getting into the practice of using the table is it's practical. We're also going to use this in other chapters. So it's going to come back. So we are adding sodium hydroxide. And how much of it are we adding? So we're adding 0.010 moles. So this is a base, which reacts with the acid part of the buffer. So we will write the acid part of the buffer. So that should be this. And then again, this is neutral. On an exam, I would ask you to, or on a quiz also, I would ask you to write out the before-after table. All right. Oops, I don't know how much stuff was in the buffer, so I need to go back here. Okay. You know, I'll just make this smaller. That'll work. All right, so I had 0.20 molar. So I had a 1 liter buffer, so I have that much in there. And I had this many moles of ammonia. And I added 0.01 moles of hydroxide. Now there's an extra 0 here, but I'm going to lose that 0 anyway when I do this. So there's our results of our before-after. And then I can say pH equals pKa plus log of base over acid. And so that's going to be, I've already forgotten what the pKa was. I'll just calculate it again real quick. So there's my Ka, or I'm sorry, that's Kb. So minus log. And then that added to 14, or subtracted from 14. So I have 9.25 plus log of, what's the base? This is the base over the acid. So we'll punch that in the calculator here. 0.51, 0.19. We're going to log U and add that to 9.25. There you go. Is that really what I got? Oh, yeah, that's right. Okay, yeah, it should be 9.68. Because I added hydroxide, and initially it was 0.965. And again, be careful. This is the part that will get mixed up. If you flip these two numbers around, then you would get... What would you get? Let's see here. Oh, that's not what you'd get. You get a much smaller number, actually. You get 8.82, so... So yeah, be careful. I was trying to find your number, but I don't know what happened, actually. All right. So that's how we play around with the HH equation. We're going to do more of this next week. So I'm going to, oops, we'll go back to over here. I'm going to have you just try this problem on your own at home. It's more or less the same problem, except it's 30 mils of 1 molar HCl. So we're adding like 0.03 moles or something like that. Same problem. pH should go slightly up. Or sorry, not slightly up, slightly down because it's acidic. And then we return on Monday. We're going to talk about buffer capacity and also how to make a buffer. So we're going to do all that. We're going to then do our titrations, and we'll be hopefully done with Chapter 14. I don't know if we'll do it on Monday, but definitely by Wednesday, and we'll finally start KSP stuff, which is very fast. So that's where we're going to start there. All right. I do want to thank everybody for coming out to the lecture. If you have any questions that I can answer, I will be available in the Discord Wednesday and Thursday. We do have the exam on Friday. Again, make sure that you aren't late to the exam because you don't want to interrupt other people. Like, that's just rude. We'll get started at about 9 a.m. and we'll take the exam. So, yeah, that's what I got. Have a wonderful rest of your week. Make sure to get the quiz in tonight or bring a paper copy on Friday, and then we'll see you for the exam. Good luck. We're all counting on you.